him that the last time he sent the money, it was not enough to buy all the provisions.
Oh, sorry, I forgot to tell him.
Are you guys talking about money transfer to buy provisions?
Yes.
But don't you know about Baluwo?
Baluwo? What is Baluwo?
Baluwo is a service that your son can use to send provisions directly to you guys from the shop. And you don't have to worry about the exchange rate.
Tell me how Baluwo works.
It's very simple.
Just log on to baluwo.com and shop, or download the app on your phone. You can shop on the website or using the app to buy online basic products for your family and friends. With Baluwo, you decide what your money is spent on. Your money, your choice. Buy online products for your family and friends in the Gambia, Senegal, Nigeria or Mali. Baluwo, better than sending money.
Hi, my name is Buba Gajigo and you're watching Kerfatu. This is your educational program, and now we're gonna bring you lessons from senior school. If you have your kid attending senior school, get them prepared, and I hope you enjoy these lessons.
Are you thinking of owning your dream homes? EJ Investment is here for you. Secure our quality bungalows with 2, 3 or 4 bedrooms, or our story buildings 3 or 4 to 5 bedrooms at very affordable prices with flexible payment plans at our Sanyang Seaview Estate, where you can enjoy the cool breeze with modern infrastructure such as tar roads, covered drainage system, modern electrification with street lights, gated entrance with security posts, and social amenities such as gas station, shopping mall, medical clinic, park, schools, children daycare, and a lot more. Our dedicated team of professionals will keep the estate clean at all times, provide security and patrol team within the estate premises, install latest technologies such as CCTV, Wi-Fi, home network installation, solar panel, and power backup system. Also, check out for our additional home facilities and interior design service such as premium tiling, wall plaster, home landscape, fingerprint home lock, and a lot more. Visit our office at Senegambia Kololi Highway and get a free site visit tour, or contact us on 4464-838. WhatsApp us on 3259220. Or you can visit our Facebook page or Instagram on EJ Investments. EJ Investments, we are first in properties.
Hello guys, my name is Samuel D. Koidia, and for our lesson today we have waves. And waves, this topic can be relevant for grade 10, 11 and 12. But before we go, I want to give you the topics, the subtopics under this. First, we're going to look at the definition of the wave. We're going to look at the classes of wave. We'll look at the representation of wave, the types of wave, properties of waves, then mathematical representation of wave. We're going to do some mathematical representation, of course. Then we'll look at sound wave, particularly. It's the type of wave we want to really look at especially. And vibration in strings, we want to look at that too. Echoes and reverberation, we want to look at that. Resonance, and the electric bell experiments, trying to demonstrate experiment to verify that we need air for sound to be heard. So basically that's what we're going to look at. Well, let's start with the definition first of all. The big question is, what is a wave? A wave is a disturbance that is propagated through a medium of space, transferring energy from one point to another without the permanent displacement of the particles of the medium. What is the meaning of that? I can give an example. Water wave. If you're at home You can just demonstrate that. Maybe you put water in a cup, settle down a little bit, and you drop stone there. If the bowl is wide enough that you can see the ripples, you will see a disturbance in that water. That is the meaning of that disturbance. There was a disturbance in that medium. The matter medium was perturbed because you drop a stone there in the water. If you look at the surface of the water, you see ripples. Ripples, they are propagating the energy. This disturbance is propagated through what? The water medium itself. So the medium, so if you look at the water, you will see the ripples in the water, and the water is serving as the medium. And what is this medium doing? It is transferring the energy, from one point to another. You know, when you drop the stone inside the water, this stone brought some energy, and that energy is transferred from one point to another. What is happening actually is that the water molecules will just vibrate. They are not going to follow. They will vibrate and transfer the energy to the neighboring. They are not going to follow the wave. That is what we mean by without the permanent displacement of the wave from their equilibrium position. You know, they are not going to be permanently displaced, but they can vibrate and transfer the energy from one point to another. So take note of that. So the disturbance must be propagated through a medium or space, transferring energy from one point to another. So that is basically what is a wave. A wave, like I said, one way we need to transfer energy is like to create a mechanism that the source of energy can reach where it is required. And that source of energy can be made to pass through a mechanism. So one of the mechanisms we can transfer energy from its source to a required destination is through waves. That's why we're saying it's a disturbance that is propagated through a medium or space, transferring energy from one point to another without the permanent displacement of the particles of that medium. All right, so now we've got the definition about what, according to our subtopics, we should also look at the classes of wave. So looking at the classes of wave, we said we have a mechanical wave, an electromagnetic wave. So those two classes, the first one we said is mechanical wave. So what's a mechanical wave? A mechanical wave is a wave that requires a material medium to transfer the energy. Like my example I just gave you, if there was no water, you would not see that ripple. You should not see the transfer of energy from one point to another. Another example, it's what I'm producing right now. You are in the studio, I think you're hearing me. And you're hearing me because my vocal cord is vibrating and producing the sound wave, the sound energy. And that sound energy is sent into the air around my head. And that sound, the air molecules around my head are vibrating and carrying that energy from me, the source, and to you, the recipient. So you see that the energy is transferred from one point to another through a medium. The medium in this case is air. You need air for sound to be heard. That's why we say we need air for us to hear sound. So the medium in this case is the air. So we needed a medium for that propagation. So that wave is a mechanical wave. Any wave that requires a material medium for propagation is what is, preferably the medium, preferably maybe matter medium, is what we refer to as a mechanical wave. What about the next one? The next one is electromagnetic wave. A coin word, say electromagnetic wave. This is electric field and magnetic field. It means that around the Earth, the electric field around the Earth and the magnetic field around the Earth will cohere together and they will act at right angle. And when they interact at right angle, they will generate a family of wave. That family of wave is what we refer to as the electromagnetic wave. In short, we call them EM wave. E for electro and M for magnetic wave. So the electromagnetic wave is actually as a result of the interaction between the electric and magnetic field at right angle to one another around the Earth. So when that happens, you will develop a class of wave, a category, a group of wave, which we refer to as electromagnetic wave. And they belong to a big spectrum. Very soon I'll give you the spectrum. Now here, let's look at this spectrum first. I'll just give you an idea of how the spectrum looks like. So here, I'll try as much to see, to consider them based upon their wavelengths. And you'll see now, I'll try and see what I will do here. And so you see some difference in this wavelength. So we see there, so between this, we have a family in there, which we can see, we call it visible light. So visible light falls there, and in that visible light, you have these colors in there. So within that middle, we have a particular type of electromagnetic wave, which is very useful to us, and light belongs there, this light. So light, which we're using to see, and even plants use to photosynthesize, they belong to that part of the spectrum. All of them are part of that family, but there's one group, one part of that spectrum which we can see, and that's what we are making use of. I'm using it right now to see you, because it's falling on your head, and it's coming to my eye, and I can be able to perceive you as a human being or something. So here, the light is the one we can see. That's visible light. It belongs to that category of wave called electromagnetic waves. And this electromagnetic wave, that visible spectrum, has these colors in there. We have red, we have orange, yellow, green, blue, indigo, and violet. So see them. We have at the extreme there is a type of wave, which is the ultra. Ultra means above violet, above violet. So you have UV there. This is above that violet. You know, you can see how the wavelength is smaller as compared to those ones over there. So again, in that same spectrum, we have another wave that is before red. Before, so I can just give you space here. You see what I'm doing? If I just move this, so you see the spectrum. I just want you to link up the spectrum somehow. So in before, this is before red. Before is infra. Infra means before the red. So there's infrared, part of the same spectrum. There's infrared, that is before the red, and after that infrared, going this way, increasing wavelength. This is the direction of the wavelength, increasing wavelength, yeah, in that order. So now we look at microwave. Microwave follows, and now we have radio over there. So you can see them as they're moving. So I have the radio wave extreme here with a bigger wavelength, and the wavelength keep reducing as I'm going towards that end. We'll have infrared, microwave, followed by infrared, and we'll have the visible form. These ones we don't see, but they interact with matter, with us. So here, this infrared, then we'll have the visible form, which is the visible spectrum and contains those colors. And beyond that, we have ultra. Ultra means above. Above violet, you have UV, and UV from that wing also we have what is called the X-rays. X-rays goes in that order, and then we have gamma. There's gamma somewhere there. So what we're saying basically is that we have X-ray somewhere here, maybe you have gamma somewhere here. This is X-ray, and you have your UV there, and you have visible light, then you have infrared somewhere there, and you have micro, then you have radio wave. So you can see these objective questions. Which of the following is having a bigger wavelength to give you a series of waves? So I've helped you to be able to understand how this, so don't mind my circles, it's not too perfect, but as you can see there's a link that the wavelength is reducing as I'm going down there in this order. So if I run up this way, there's an increase in wavelength. The wavelength increases in that order. So you see this is the spectrum to which this family of wave I'm talking about, electromagnetic wave, which is the interaction between the Earth's magnetic field and electric field at right angle, generated this group of wave. And we are using these ones a lot. These ones are visible. That's, like I told you, is what I'm using to even say you. So let's see what they do. So for, you know, this topic has a whole special treatment, but because of it is part of this, I just want to give you a browse, somehow a summary of what I have just said so far. So look at radio wave, see how we interact with them as human beings. We see radio rays, we use them for radio communication and TV communication, you know. So all what you're doing now, you're watching this program on the TV, you're using a particular type of wave is concerned here. So that's radio wave or TV communications. And we see microwave. Microwave, like I told you here, look at the way they are running down. Microwave is used in satellite also. It's also used for communication in satellite. And the high frequency microwave is what we use actually in communication. You can use it in telecommunication even. So you see all this GSM, they are using the microwave there to do the communication. And we can also use the low frequency type of it, because let me just go back to that microwave. Microwave can pass through the atmosphere. So that's why it is easier for telecommunications to use it, because it can easily pass through the atmosphere. So what's the atmosphere? It's the bundle of air around the earth. That's what we call the atmosphere. And that communication is affected by that particular part of the... So that microwave is actually used for communication at high frequency. The lower frequency type is what is used for cooking, because water molecules they actually absorb microwave and they become hot. And when they become hot, that's what you need for the water molecule, because you want to cook. So we use it for cooking. That is because it is best absorbed by water molecules. So the lower frequency of that microwave is used for cooking. That's what is there, absorbed by water wave very well. And you see infrared in grills and toasters. And we also use in optical fibers. Remote control you're using to put on, the remote control you used to put on this TV as you're watching this program is using that infrared. Infrared radiation is used by the remote control, optical fiber, and also toasters and grills. They use that. And visible light, of course, is what you're using to see your friend by you right now. It is used for seeing. You use it to see. It is what is happening there is that it's the light rays falling on the head of that human being, and it's coming to your eye. And if your eye is correct, then you should be able to see. So that is visible light used for seeing. And plants also use it to photosynthesize. It's also used for photosynthesis. You see that. And we also use it for optical fiber communication. Remember, optical fiber, all these communication gadgets. You know that we'll come to that part of physics. We will talk about how the internet even works. You see, it works on optical fiber or fiber optics. You see that total internal reflection taking place inside the optical fiber, and you see the energy is transferred from one point to another. So we can use light to transfer a whole bunch of communication, a whole bunch of energy from one point to another. Like you're using in the internet much more use optical cables, and you see how the energy is transformed into that light. And that light transfers the energy from one point to another. So we see, and I've said visible light can be used for photosynthesis and also inside optical fibers. What about ultraviolet? Ultraviolet ray is used in some beds. If you go to the hotels, you have some beds where the tourists and other people, not only tourists, people that want to just relax on the beach there, you see some bed. Some want to use that particular part of that spectrum, that part of radiation, to actually tan their body. You can use it for skin tanning. It interacts with the melanin under your skin, and it will tan your skin. So it's good for sun bath. You see some people sit under the sun. So you have the ultraviolet. It's ultra means above. It's a part of this. It's above the violet, so it's part of that sun rays which is coming down, and it sees you can use it to tan your skin, as a matter of fact. Now it can also be used in fluorescence lamps, of course. Now we look at X-rays. I cannot overemphasize the importance of X-rays to our daily life right now. Some people, the doctors, use it a lot to see objects in your system. Maybe swallow metallic objects, even fractures, broken bones. You'll be able to identify it in the system of that. A particular part of it can pass through your flesh, but it is stopped by bones. So we have different types of X-rays. You have soft X-rays and hard X-ray. And the soft X-rays, you use them much more in medicine and in the hospitals. And they also use them to check structures of manufactured items, like crystals of materials. We can use X-rays also to check them. So I can leave the X-ray for now, because I'm going to go to that topic later on. But just know that it is also used in the hospital. It is used in manufacturing industries. Right? So now we look at the very last one over there, which is the gamma rays. The gamma rays is also part of the spectrum, and it is used for killing cancer. That's under the doctor's prescription. You just use gamma rays. But we can use it in the hospital to sterilize our materials. We can use it in the cooking industry. in the hotel industry to sterilize our food. We can also use it to sterilize the doctor's operating instrument. We can use that in the hospital. So gamma rays are used for killing cancer and also sterilization. So I've basically run through all the electromagnetic family. They belong to that family. The family is the electromagnetic spectrum. So I've already lined up all of them for you. I hope you're following. Now look at how this wave can be represented. You know, we have already said that the wave is, let me just clean here so we see how we can represent the wave. Now, we said it's a disturbance that is propagated through a medium or space, transferring energy. You know, transferring energy from one point to another without the permanent displacement of the particles of that medium. So if I'm coming to represent that wave, the wave representation of wave, so if you want to describe a wave, we first of all need to represent the wave, and it is represented, let's say, by series of elevations and depressions. Elevations and depressions. What do I mean by that? It's a big mathematical term, so I can continue if you like. So here we have this wave that is being represented. This is a vibration. It's going to be represented by series of horns, elevations and depressions. So now the particles will be displaced up first, then later it comes down. So there's a level where these particles will have a maximum displacement. So that maximum displacement is enhanced by a particular distance. So that distance here, along this displacement axis, it's called the amplitude. So the first terminology we want to talk about first is the amplitude of the wave. But before we get to the amplitude of the wave, I want you to know that this wave, what I've drawn here, is representing a progressive wave. So like the wave is transferring the energy from one point to another, and it is progressing. This disturbance is carrying energy from one point to another, and it could be transverse and longitudinal. I'll get to that very soon. So let's see what is the representation proper. So I'll just give you some terms here. I'll give you some terminologies here too. So we have this, and if, in terms of period, the distance covered from here, the time taken for it to cover here will be classified as the period. But now I'm using displacement axis, x in meters over there, and it's doing the y displacement somewhere there. So it says it's like what I was saying. I've just given you a picture. So I'm using that picture now to define the various terms there. If you can go back to the picture, you just look at that picture, and there is a point where the displacement can actually be at a very big peak. That point is called the crest, we know that already. And there is a point where the displacement in the opposite direction is minimum, and that minimum displacement is at a peak called the trough, and we have the crest and the trough, or the maxima and minima as the name comes. So here, that maximum point where the displacement is as massive is what is called the crest, and that crest is also called the maxima. So we have maxima, which is crest, and we have minima, which is trough as well. So we look at the first terminology. That's an amplitude. What's the amplitude of the wave? It's the maximum displacement of the wave. Remember, I said it's the disturbance. The wave has to be disturbed. And as you disturb the wave, the particles of that medium are being disturbed, and they are going to vibrate, and they will move to a bigger displacement. That maximum displacement from their rest position is what is called the amplitude. So the amplitude is the maximum displacement of the wave from the rest position or mean position. So this is their mean position. So when you drop in the stone inside the water, you saw the water molecules vibrated, and they went to a maximum height. That maximum displacement of the wave from their rest position is what is referred to as the amplitude of the wave. So this distance on this picture is what is defined as the amplitude of the wave, and it is measured in meters. Very soon we'll begin to interact with them, so take note. And number two is the wavelength. What is the wavelength? The wavelength is the distance between consecutive crests. Remember, I just told you here that there's a crest somewhere here, there is a trough somewhere here, and there's a crest somewhere here also, and there's another trough. So now the distance between consecutive crest and consecutive trough is specified, is described as the wavelength, and that wavelength is is actually, let me be writing it here so far. So you see, that is, and it is measured, it is A measured in meters. And the next one from our exposure, there is like a wavelength. What's the wavelength? I just told you. Wavelength is actually represented by that Greek letter. It is also measured in meters. Now, that Greek letter is lambda. Lambda. Now, lambda, which is a Greek symbol, is representing wavelength in this our situation right now here. So we have wavelength as the distance between consecutive crest or consecutive trough. So it's either this distance here or this distance there. So that distance gives you the wavelength of the wave. What about if this, since it appears as if it's a periodic repetition of cycles, then we'll talk about the period of the wave. So what is the period? The period is T. The period is, as we know, is the time it takes a particular object to traverse a complete circle. So the time it takes this wave to traverse a circle is what complete circle is what is called a period. We know that already. So what's the period? The period is the time taken by a particle of the wave to conduct a complete circle or complete oscillation. So here, if I consider this axis as a period axis or time axis, I can say this time it takes this wave to traverse this. This is a semicircle, so we'll have a full circle. The time it takes to traverse that length, these two semicircles to form a circle, is what is called a period of the wave. So now you know what is the period of the wave. It has a basis with actually the frequency of the wave. So that leads you to the next terminology, which is the frequency of the wave. What is the frequency of the wave? The frequency of the wave F. Remember, the period is also measured in seconds. As a matter of fact, you know that is in seconds. And the frequency of the wave is the number of circles or oscillations which the wave can make. Remember, I said the frequency is the number of vibrations, circles, oscillations. It's done per unit time. So if I want to know the number of vibrations, if I know the number of vibrations, watch out for this when we go to the questions. You see this formula coming. We'll have the number of, so let me use n for that and that. And this says the time, the frequency is the number of vibrations or oscillations or cycles made by the wave in time, unit time. So now, if that is the frequency, then it has some connection with the period. So, and the period will actually be the reciprocal of the frequency, because it's the upside down of the frequency. And that's, if I substitute this into that equation, then I'll find out that I'll have a link between the period and that time. That is why we said in simple pendulum that the period has a link between this. So if it's just the reciprocal is upside down of this. If I substitute this into this equation, I will get something like that. So now we'll have the period as also giving us the time over the number of circles the wave makes. And remember, there's a link between the two of them. We have the frequency and the period, they have a link between them. And the frequency is measured in hertz. Remember that? It is measured in hertz. And it is Hz. It is measured in hertz, which is Hz. So I've just given you a notation over there, so we can see what happens with the period. So I'll go back to the progressive wave again. We say it's a disturbance which is carrying energy from one point to another. It could be transverse wave or longitudinal wave, remember that. But I have just brought in basic terms here. The first one I said is the amplitude. The amplitude of the wave is the maximal displacement of the wave from its rest position, so understand that. And I've said also there is what is called the wavelength, that is the distance between consecutive crest or consecutive trough, or between consecutive maximas or consecutive minima. So we have the crest is also called the maxima, remember that. So the distance between consecutive crest or consecutive trough can be referred to as the wavelength, and that wavelength is measured in meters, remember that. And I said the amplitude is the maximal displacement of the wave from its rest position. And the frequency is the number of circles, oscillations, vibrations which a wave makes per unit time. Gives you the frequency of the wave. And the period is the time it takes the wave to complete a circle. That's the period, you know that from scratch. So we now have other terminologies I didn't state here, but I think you know I've come across those ones. The wave can have speed. If you want to talk about speed, normally we always talk about the distance something covered per time. So if I look at the wave speed in this case, we call it the distance the wave travel in unit time. So in this case, we call it wave speed or wave velocity. Remember speed and velocity. So we have velocity as the displacement. In this case, we call it distance because we are using speed. Speed goes with distance and displacement goes with velocity. Note that. So here we have the speed of the wave. It is the distance which the ratio of the distance to the time traversed by the wave. It can be measured in meters per second. You know that already. So now we can also have the phase of the wave, or wave phase, you know, or wavefront. So we have the wavefront. You know, there are particles on the wave that are having the same displacement from the source. When particles that are progressive, that are having the same displacement from the source, the connection between those particles will form a locus. That point connecting common points that are of the same displacement from the source can be referred to as the wavefront. So we will keep those terms for now, and we just concentrate on the relationship between the two of them, all these three terminologies. So what I've just stated sometimes here, I want to bring the relationship between all three of them, or four even. So check, I said the speed, the wave speed, in this case, we said was the distance or displacement time. And we've already said if the guy completes a circle, it completes a circle, it's already a circle here because this is a quarter circle. This is a quarter circle. This is a half circle. So quarter and half give you full circle. So we have lambda, and the time it takes for this wave to traverse this is from here to here is also a period. The time it takes, because it's a full circle. This is quarter circle, semicircle, put together will give you a full circle. So the time it takes to complete a circle, we said it was called the period. So it was represented by T over there. So now we can now link up the two. We said V is lambda over there. That's one equation that is going to be prominent in our calculation. So watch out for that. And we said we know that T is this is the period. The period is the reciprocal of the frequency. So we can put them inside this equation. We'll have V as equals to lambda over the reciprocal. So this will give you, if you do the math, you have something like this. So the period, the speed is related by the product, is equal to the product of the frequency of the wave and the wavelength of the wave. And that speed is measured in meters per second. Note that. So now I can go back through these small formulas so that we're going to use them to solve our problem. First, I said amplitude is the maximal displacement of the wave from its rest position or main position, note that. And I said also that the wavelength is the distance between consecutive crest or consecutive trough. And I said it's measured in meters, remember that. And I also defined the time taken for the wave to complete a circle. It's called the period of the wave. And I said we also have the frequency of the wave, that the number of circles that wave makes per time, per unit time, or the number of vibrations the wave can make in a time. And that is what is called the frequency of the wave. Now we have a connection between the terms. You can see from the proof over there that the wave speed, which is represented by V in this case, is equal to the frequency of the wave and the wavelength. So we want to use these equations now and solve a few problems. So you see example 1 from the board there. We'll see. Let me clean here so we try and create space for the emphasis. So looking at the first example, it says that what is the wavelength of a wave traveling with a speed of 6 meters per second and a period of 3 seconds. So remember, now we said there are basic terminologies here. I want you to note them from that point there. So we say lambda over T And from that, we are able to specify that. Remember that. And we say also frequency is a number over that. So remember these formulas here. So it will help you out to figure out what I'm saying. So the first question says, question number 1. So let's collect the data. It says the wavelength of this wave traveling. So we'll have to find the wavelength in that question. So it says, what is that wavelength? Yeah, and he gave us the speed of the wave, that is that. And now he says also the period of that wave is given. Remember, this is the period of the wave, it's not the time. So it's period of the wave, that. But there's a link between the wavelength, the speed, and the period of the wave. So now we can link up this equation and let's find, say, what is the wavelength? So we needed to verify the wavelength, which is Vt, if I use my equation here. So you now have the V was what? It is 6 in that question, and you have the period. Remember the period here is 3. So we now have 18. And we said this one is measured in meters. So lambda, which is the wavelength of that question, is 18 meters. 18, speed 6, and the period is not this. This is not the time, it's the period. The period is the time it takes to go around a complete circle. So we go to question number 2. It says a fisherman noticed that a float makes 30 oscillations in 15 seconds. The distance between consecutive crests is 2 meters. Now, what is the speed of the wave? So watch this second question. So I can go the number of oscillations made in that question. It says the fisherman noticed that he's making 30 complete oscillations in a certain amount of time. The time was 15 seconds. Now he says the distance between consecutive crests is given by, this question is 2 meters. Now he's asking you to find what is the speed of the wave. Watch that. That is the speed of the wave. So if you look at speed of the wave formula, we say speed of wave is frequency lambda. So now if I want to get the frequency, if I want to get the speed first, I need the frequency. The lambda is already in the question. So I needed to go and find the frequency of that wave. Remember, I said the frequency is the number of oscillations that float is making. If you go to the around Tanje, you see this kind of thing happening. If you are on the fisherman's fishing boat, you will see the float. The float is making an oscillation. Oscillation is to and fro movement. So you see that oscillation, that float is making 30 complete oscillations per 15 minutes. So now it was oscillating 30 times, number of times it was oscillating, that is to and fro on the, some of you have seen that on the sea when the float, or you that do the fishing, you know what I'm saying. So how the time is that, so the frequency in this is 2 hertz, because 30 divided by that will give me 2 hertz. But I'm not interested in the frequency, I'm interested in the speed, because the question says what is the speed of the wave. So now I know my frequency, which is 2, then I know the lambda, which was given there. So I can have the speed of the wave is 4 meters per second. So speed is measured in meters per second. So you can see from there that we have already done the first 2 examples. So now let's take one more, then I can give you some assignments which you can also interact with. Okay, these are the questions I've already solved so far. See that? Question 1 is what I've solved so far, and question 2 is also the same I've solved over there. So you can see the 2. Now let's take number 3. Number 3 says what is the speed of the wave? The period is already given to you, and the wavelength is 1.8. You say what is the speed? So you can look at this equation. The speed is there. So I want to give you as your own classwork, but I've already helped you with the formula. You say what is the speed? What is the speed of that wave? And it says the period is 4. The period is 4. The period is 4. And it says and the wavelength is 1.8. So for your own exercise, I've just directed you into that solution. So number 3 on that It's your own classwork. If you can do it in 1 minute, then that's cool. I've collected the data for you already. So now we'll look at the types of wave. Now, it's looking at this, we've already looked at the types, or we want to look at the types of wave. Remember the classes I gave you? I just gave you a broad classification of the wave. We can put them in those two classes, a mechanical wave, which requires a material medium. And I wanted to ask one simple question. If there is an explosion in the sun, is it possible for us to hear that on Earth? So I want to ask that question. So think about that question. If there's an explosion in the sun, is it possible for us to hear it here on Earth in the sun? Remember the sun is a compact mass of gas, it's right up there. So if there's an explosion in that sun, you on Earth here, can you get that sound? Because I want to say it's related to what we're doing here. So remember, I have classified the waves. I told you there is mechanical wave, require a material medium, and we have the electromagnetic that do not require matter medium. It can propagate through matter and live in empty space. But now we are going to the types of wave. The first is transverse wave. Remember that? Transverse wave. So what's that transverse wave? You know, a transverse wave, in the first place, I want to just categorize them straight. All electromagnetic waves, these ones I just stated here just now, are all transverse. Because I just told you the foundation of these waves. I said it was electric and magnetic field that cohere together at right angle. So right angle is 90 degrees. So because of their interaction, how they propagate, you can see. So now all waves that have that way of propagation is in the form of transverse order are those ones we are going to talk about here. So what is this transverse wave? It's a wave in which the pattern of disturbance is at right angle or perpendicular to the direction of the wave motion, meaning the vibration of the particles of that medium are going to be vibrating in one direction, let's say vertical direction, and the wave they generate will be moving in the horizontal direction, such that the wave will traverse the mode of vibration. This is mode of propagation and mode of vibration. The mode of vibration and the mode of propagation are at right angle to one another. Right angle is the same as perpendicular, 90 degrees to one another. So why do we have to consider their mode of propagation here? You know, don't confuse what I said just now. I just said all electromagnetic waves are transverse, but that doesn't mean that there are no other transverse wave. Water can be transverse. You know, if I drop stone in the water, now the stone goes this way inside the water. Now you see the particles of that water will vibrate vertically. They are vibrating in this order. But when you look on top of the bucket or on top of the pond or on top of the sea or anything, you will see that the propagation of the wave is in that direction. So when the vibration is in this form, that's the mode of vibration is this way, the propagation will be in that order. So it means that if I vibrate, the molecules of that medium will be vibrating this way, and the wave generator will be vibrating in the other way. So it's going to be at right angle to one another. When that happens, we talk about a transverse wave. That picture tells you, that's just what I've told you. This is the vibration of the particles are going to be in that form, and we have the propagation of the wave. Yeah, we can see a few examples, like I just told you. Now, all electromagnetic wave, including light, all forms in that category I just told you. That water wave can be an example of that. And wave form on a rope even, or a spring. I can plug a spring. I can plug, let's say I plug the spring. This is spring. When I plug the spring can go that way and can be, so the molecules of the spring we vibrate vertically, and the propagation will go in that way. So a plug spring reform on a string or a spring can also generate a type of transverse wave. But just note that the transverse wave, the vibration of the particles of that medium must always be in perpendicular to the mode of propagation. That the vibration and propagation must be perpendicular to one another. So note that type of wave. That is an example. All electromagnetic wave, including light and water waves and waves on springs, or strings or ropes are all that type of wave called the transverse wave. Now, what about the second type? The second type is the longitudinal wave. Remember, longitudinal wave. So longitudinal wave is that type of wave in which the mode of vibration and the mode of propagation of the wave are in the same direction, or they are parallel to one another. The mode of vibration and propagation are in the same direction, or they are parallel to one another. So what do I mean by that? Now, in this type of situation, you will find out that the molecules of that medium will be vibrating in this direction, and let's say, for instance, waveform on a spring. So we have, you can see from my strings, there is a point here. These molecules will be vibrating in this direction. They'll be vibrating that way, and the wave motion is in that direction. This is the wave motion. And this is the vibration, mode of vibration. So the molecules of that matter will be vibrating in the same direction as the propagation. Right? So now you can see from that point that the molecules are vibrating in that form, and the wave is generated that way. So example of this type of wave is the sound wave I'm producing right now. The molecules of the air, the air molecules around my head are going to be vibrating in this direction, and they will send the wave in the same direction, and it goes to your ear, and your ear perceives that as sound. So sound wave is an example of longitudinal wave. And you can see on this model here, you can find out that if there is a point on this spring where the spring, the molecules of the spring will be suffering from some pressure, so they will compress together. When they compress together, that's the molecules will come to close to one another, and it becomes compressed. That point the pressure is high over there. That point is called compressions, and they will relax again. And when the molecules relax, and they will compress again, they relax and they will compress, and so on. So it's a series of this compression and refaction. This part where the pressure is low, they relax a little bit. It's called refractions, and we have compressions. It's a series of compressions that transfer the energy from one point to another. As you can see, note the mode of vibration. The mode of vibration and the mode of propagation are parallel to one another. In transverse wave, they are perpendicular to one another, but in longitudinal wave, they are parallel or in the same direction. Watch, look at this spring there. There's expansion on the spring, and there's a point where the spring becomes compressed. That is the same thing that's happening now as I'm talking to you. The air molecules around my head are taking the energy from me to your ear so that you can perceive, you can hear me. So what is happening, you in this studio I'm referring to, you see the molecules of the air around my head are going to be compressed. That is, the pressure is increased, and they relax again, they compress, relax. As that series of compression and relaxing of those air molecules will transfer the energy from one point to another. That is the longitudinal wave for you. And we have example, I just gave you, an example of that type of wave is sound wave from simple noise or note from instruments. You sound, for as much as you produce sound, you are a longitudinal wave. Now we look at wave on a slinking string, like what I've just given you. This is a slinking string. If you drag it that way, you see the slinking nature of it. That is a longitudinal wave. The third one is going to be standing wave. We'll see in that case. So we'll have stationary, standing or stationary, standing or stationary wave. Stationary wave. So for standing or stationary wave, what happens is that, let me draw here so you see the picture for transverse. So I want you to just see it from the board as I'm moving, this vibration there. So I come back to standing wave. We say standing wave are produced when two progressive waves of the same amplitude and wavelength, maybe even the frequencies, and traveling in opposite direction, and they superpose. When coming together, they superpose. That is coming together, combining together, and interfering. When that happens, we will see a standing wave. Now, the standing wave actually do not progress. it's confined to a place. But the molecules will still vibrate, never mind. But the wave is confined to a particular space. That's what they call the standing wave. The type of wave is seen on a pluck spring. If I have a string or a string that is tied at both ends, then I pluck it, you will see the wave will go up to the end until it will come back. So the wave is confined to a specific position, a stationary position. That's the reason why we call it standing wave. Example of that kind of wave is what you see on this rope. See this? This is an example of what I'm saying. The string is having two ends over there, and there is somebody holding it over there, and you see it's tied onto that wall or something. So you see when you pluck it, you see transverse wave. You will see waves that are moving, but when this wave returns back, you will see that this progressive transverse wave will superpose on one another and they will form that standing wave, and you see series of loops over there. Let me just give you an idea of how it looks like. This is a standing wave, for example. So the standing wave is two progressive waves moving in the same medium, and they are moving in opposite direction. When they superpose, they generate this type of wave. So you can see there is a part of the wave where the particles appear to be stationary. That part of the wave, there is going to be little or no displacement. That part of the wave is called, so there is momentary rest of the particles there. There is no displacement of the wave at that point. So we call them the rest position of the wave. That is, the particles are at rest in that point. So we'll have there and there. So we'll have that point is node, that's another node, that's another node. But there's a point on this profile where you see the wave suffer a maximum displacement. That path where the wave suffer maximum displacement is anti-node. So there is an anti-node, there is a node. So a node is where there is little or no displacement. No displacement, that's the wave is at rest, and we'll have the anti-node. The anti-node is the point where the wave suffers maximum displacement. And the distance between two nodes form what is called a loop here. There's a loop here. Yeah. And the distance between consecutive antinodes will give you quarter, that's half of a wave. So it's going to be half of a wavelength. That's half of the wave particle that you see. This is a quarter here, this is quarter here. Quarter will give you half. So watch out for objective questions as you are entering into it. So this kind of wave is the wave generated by that string went up to that point and returned back. So it's the two waves will superpose as it goes to the end and return back, forming node. So there's a point where the particles appear to be in at rest position. That's a point called node, and the other point is called anti-node. So watch. Now we have the wave will form these loops. These circles are called loops. So what's the connection between the loop and the number of loop and the wavelength? I've just told you that this is a full wavelength. That is a full wavelength here. This is a half of a wavelength. So now for a standing wave, the distance between consecutive anti-node cannot give you a wavelength. So note that. So now watch here. The wavelength and frequency of standing wave can be compared with this equation. So the equation that links the two is given by the times the length of that wave and the number of loops. So here L is the length of wave, and N is the number of loops. Right, remember, this is a loop, this is one loop, that's a loop of a wave. So this wave contains two loops, of course. So now we look at the equation that connects them. Remember, this is the length of the wave. This is, so if I could put something here to represent just that, this is the length of the wave, and that length of the wave, and N is the number of, so what is the relationship between the length of the wave and that of the wavelength? So it's given by that. So if you can come back to your speed of the wave or the frequency of the wave, we can verify. Remember from our equation, V was frequency lambda. All right, so now if I want to find the frequency, is V over lambda. And remember, I have already said this is it. So I can find V all over this guy is this. So I put 2L over N. So the frequency is going to be equals to N, if you like. and I just transpose that guy over, so I have 2L. So you can find this, and if you look at this, it's just the reciprocal of what I've said so far. So you see N, that, so we have the relationship between N, V over that. That's the equation I've just given you over there. So now you'll be able to use that equation, and remember this N can take different loops, different numbers, like N can take different numbers, one going upwards like that. So we have a relationship between them. Let's say, for instance, I want to compare. Now, let's say this length, this wave is having a length of 4 meters. So in this question, let's say the length of that wave is 4 meters, and the loops, number of loops is 2 in that case. So I have 2 loops over there. So I can find the wavelength is related by 2L all over N. Remember this formula as I'm moving up. So this wavelength is going to be 2 times that guy over there, which is 4, divided by this other boy here. So we'll have lambda as equals to this will go. So I have 4 meters. So there's a link between them. So if this N is the number of loops, remember the 2 came in because there are 2 loops. So we use the same equation to solve a few examples. So watch out. Now we'll look at that. They say, what is the wavelength of the wave shown below? So watch. If you have the wavelength of the wave shown below, you can see from that question that I have 5 loops. So again, question number 1 on that page there, let's say question 1. On that page we have, what is the wavelength of the wave shown below? So this wave contains 5 loops. So I can just draw them for you here. 2. Now this wave contains 5 loops, and the length of the wave is 5. This length of the wave, L, is 5 meters. So it says, what is the wavelength? The wavelength is 2L over that. So you now have 2 times, the length is 5, and this guy has 1, 2, 3, 4, 5 loops. Each circle there is a 5 loops, so you have 5 there, and you have the wavelength as 2 meters. So that is the wavelength for that question over there. Now you have a few that you can do to say, what is the wavelength of the wave shown below? So you see the wavelength, you can continue with the same logic over there. You have number of loops here, it's still 5 loops, but now this the length of the wave is changed in this case. You now have number of loops. You can go back to question number 2 in that case. It's a number of loops there, so let's count it. It's 1, 2, 3, 4, 5 loops there. So we'll have 5, and it says find the wavelength there, and the length of the wave is already given to you. The length of the wave is 10 meters. So you say, what is the wavelength? Remember the connection between, so we'll have that. So we can fix, so we'll have 2 times 10 all over 5. So we'll have this entry here, so it's T4 lambda. Now the next slide is your own, I'll be reading it out, it's assignment for you. So let me read this one. I think I've solved this already. So I go to this one. This is, what is the wavelength of the wave shown below? So if I can count it for you, we have 1, 2, 3, 4, 5 loops there, and the length of the wave is 10 meters. I think you can do that using the same formula. The next one is saying, if the speed of the wave is 8 meters per second, now what is the frequency of this wave? Remember, the frequency of the wave is related by that, the speed and frequency is related by V equals to frequency lambda. So you see here the same wave, it is having 5 loops and the length of the wave is 10. I think you can do that. After finding the wavelength, you substitute inside the equation V equals frequency lambda. I think you can do that. Now for summary, we want to just recap a little bit before I end the lesson. Now we said the vibrating objects are sources of wave. We did that before. That's why we define wave as the process by which a disturbance is caused into a matter medium, and that matter medium transfer the energy from one point to another without the particles of the medium following the wave. And we are able to look at the wavelength as the distance between consecutive or successive crests, and we looked at the number of crests and that passes a given point at unit time is what we call the frequency. We define all of that. Amplitude is the maximum height of the crest. We did that, and I was able to give you that relationship as V equals to frequency lambda. And we also defined transverse wave. We said It's perpendicular oscillatory. The oscillation is perpendicular to the direction of a wave motion. That's what I said. I said it is the type of wave in which the mode of vibration and propagation are at right angle to one another. And look at the other one, it's longitudinal wave. We say longitudinal wave, they are parallel or in the same direction. Now we were able to summarize and link up the length of the wave and the number of loops created relating to the wavelengths. You see that equation over there? And we know that waves always transfer energy. So note that. That is the basics there, the wave transfer energy. So we'll stop here for this lesson and we'll continue again. Thank you for your audience.
Hello viewers, these are key messages from the Ministry of Basic and Secondary Education on the coronavirus. Dear parents, keep children at home at all times. Avoid sending children to shops and markets. Do not engage children in petty trading on the streets and garages. Allow children to play within the confines of the home. Limit visitors into your homes. Adhere to COVID-19 health precautions and guidelines. Schools are closed, but learning continues. Dear teachers, you are encouraged to desist from all forms of group activities involving students. All school premises should remain closed and not to be used for any other purpose. Thank you.
In communication, connectivity is everything. We ensure that the links never sleep. Quantities and qualities all in our data service, providing efficient, reliable voice and data service. We believe if you're not up to speed, then you're going backwards. Communications have to flow as fast as the speed of light. Whatever business you're in, having someone who understands your needs is critical. That is why we just don't offer you technology, we offer you solutions. Enjoy Gamcel's internet broadband anytime, anywhere. Your national operator, Gamcel, Yaibaram.
I get it. Albaka.
Mbaka important.
Yo, nga transfer la story.
Ya transfer la
ha code nyinji.
Okay. Nsila ID soto.
Sorry. I get it.
Bijan bro.
Albaka.
Mbaka.
Bara alla service o tariya. Mbare ki janna nun kunu bara tariya.
Janno yona forest de bureau. Gambia tonkon na no mbari ya bere. Birim koyna fo kato.
Bari si kodo kino kato ni fo bolong blabe fo.
56 branches mola sota Gambia jam.
Ha?
Gambia kono ani Gambia bantala bankol. Nko kodo kiya bere. Kodo sifa fo falindiro fo nyaadi lafta même na kodi to poto ni kodi maraw. Jannam number 1 di nyonta. Andum fana nata anoda enterprise sotale. Wolam nyindi ko domorol fana kol fana be firale le dadi mani domorol ni fana beteat. Gambia dawda yalo ngam fa kendol sotale je.
Wo moyo diat ha.
Apelenta
ni
baraka
ni lafta nyelen kendol e bina.
Yalo bukani la ko la baraka ba.
Yalo ndel chosano lo.
Abaraka.
Touchdown, but I broke down.
Gamtel G-Fiber, now you can enjoy super fast internet in gigabytes. G-Fiber is affordable, stable, secured, and accessible to homes, businesses, and enterprises. With Gamtel G-Fiber, the future is speed. Gamtel, creating a brighter future in communication.
So she became mine and see the
Yara nyilla domoro kadiyata.
Boy, janno Sikes restaurant.
Sa na ko be ni na dimbal. Nimba domoro kala janno.
Domoro seneyata adiyata topotoro fanan kende ma bije. Luntan during tamala abeka domoro ki janni. Adi manda wala de. Teka we bijele anim fanan ka fadi jang ikono e fa. E ka fa minne ko pastry anim bakery. iko fanan be kalele badde lomba conference lomba workshop lomba ye fo fendin lon dunia kono domoro betama nyillom international o toda number 1
amanke ba domo la jang damman
esa domo jang is atariya
wo mu kubandi
sa na ko sa futandin
oto sa na ko be mu CK's restaurant
dafa nan janna mu yat ni manje dorom bijam
aban
CK's restaurant, known for best quality food and customer satisfaction.